Yes, one point to remember here, to derive the deflecting torque equation of MI instrument, that is moving iron instruments, then we can use one concept, that is according to law of energy conservation. We know that in MI instrument, in moving iron instrument, there is one electromagnet. Okay. Based on this concept, I am writing one equation. Based on that equation only, we can derive the what is the torque equation of MI instrument. Okay. In this MI instrument, there is one electromagnet. Yes. This is one electromagnet. Then, whenever supply is given to the electromagnet, this electromagnet will be magnetized. It produces a flux, this electromagnet will be magnetized. Whenever electromagnet is magnetized and there is a spindle, soft iron disc means it is made with nickel and iron alloy in order to reduce the hysteresis losses. Then because whenever supply is given, this electromagnet will be magnetized, then it produces the attraction force on the iron disc. Because of that attraction force, the pointer is moving on the scale. Okay, this concept you know in moving iron instrument. That means according to this concept, I am writing one equation according to law of energy conservation. Yes, whatever the electrical energy input we are giving, that electrical energy input is responsible for two works in the case of moving iron instrument. One work is for magnetization of this electromagnet. The another work is deflection of the pointer. Understood? Then the total electrical energy input equal to change in electrical energy in the electromagnet plus deflection of a pointer. Deflection of a pointer is nothing but a mechanical work done. Okay. Then according to law of energy conservation, you write this equation. Listen please. Write down this. Therefore, electrical energy input equal to electrical energy input equal to change in stored energy. Okay, change in stored energy, that is magnetization of this one. Change in stored energy plus mechanical work done. Mechanical work done. This is according to law of energy conservation. Let this is equation 1. Electrical energy input equal to change in stored energy plus mechanical work done. Now, let the supply voltage is V, the current is, the operating current is I, where I is the operating current, V is the supply voltage. Whenever supply voltage is given, there is a current is passing through the coil. A coil is nothing but a, just like inductance na. Then tell me, how to write? The voltage across the coil or inductance, V is equal to L into di by dt. V equal to L into di by dt. But if the input is changing, current is also changing, flux is also changing, inductance is also changing. That's the reason why in this case the inductance is not constant. That inductance is changes according to current through the coil, that is according to deflection of a pointer. Then how to write d by dt of Li. Now from this how we can write L into di by dt plus I into dl by dt. Okay. Now from this shall you write like this, V into dt equal to L into di plus I into dl. Multiply both sides by I. Then what we get? Vi into dt equal to Li into di plus I square into dl. What is Vi into dt? voltage into current into time, that gives the energy. Okay, this is electrical energy input. Electrical energy input. Let this is equation 2. The electrical energy input equal to VI dt equal to Li into di plus I square into dl. This is electrical energy input. Now I want to calculate change in stored energy because of given supply. How to calculate change in stored energy? Let us assume that initially the current is I, inductance is L, then what is the energy stored equal to half Li square. The energy stored in the inductor is nothing but a half Li square. Now the current is changing from I to I plus di. Because of change in current, there is a change in stored energy, then there is a change in magnetic field. Once the flux is changing, what the inductance is also changing. Let the inductance in the coil changes to L to L plus dl. Now what is the energy stored in the inductor? Half L plus dl into I plus di whole square. I plus di whole square. Then what is the change in stored energy, you tell me? Change in stored energy is nothing but a final energy minus initial energy. Okay, change in stored energy. Yes, change in stored energy equal to half into L plus dl into I plus di whole square minus final energy minus initial energy, half Li square. This we get. Then by simplifying and neglecting higher order terms, by simplifying and neglecting higher order terms, by simplifying and neglecting higher order terms, then what you get to tell me? Therefore change in stored energy equal to then how you can write? By neglecting and by simplifying and neglecting higher order terms, this we can get half I square dl plus L, this half I square dl plus Li into di. This we can get. Let this is equation 3. Change in stored energy equal to half I square dl plus Li into di. This is equation 3. Okay, but we know that, let us consider initially the pointer is at current I. Now the current is changing from I to I plus di. Because of change in di current, let the change in deflection of a pointer is d theta. This deflection of a pointer is because of some torque now. Let the torque is nothing but a deflecting torque Td. Okay, then because of change in current, there is a change in deflection of a pointer because of due to some torque. Then there is some mechanical work done. Work done is nothing but a, that is a force into displacement, but here instead of force you take the torque into angular displacement. Then what is the mechanical work done? Yes, mechanical work done equal to how much mechanical work done? Okay, the mechanical work done equal to Td into d theta. Let this is equation 4. The mechanical work done, how much mechanical work done? Force into displacement. The force into displacement is nothing but a Td into d theta. Now substitute equation 2, 3 and 4 in equation 1. This is equation 1. Substitute. Yes. Substitute equation 2, 3 and 4 in equation 1. Then what you get? Tell me. What is the electrical energy input? Electrical energy input equal to Li into Di plus I square into Dl is equal to, what is the change in stored energy? Change in stored energy equal to half I square into Dl plus Li into Di plus mechanical work done Td into d theta. Td into d theta. Then this Li di cancel. This is I square into Dl minus half I square into Dl is equal to Td into d theta. Tell me, this is I square Dl, this is half I square Dl. Then how much you can get? Half I square Dl. Then half I square Dl equal to Td into d theta. Then from this, what is Td equal to? Half I square Dl by d theta. Okay, this is the deflecting torque equation of MI instrument. Yes, this is deflecting torque equation of MI instrument. This important equation. Td equal to half I square into Dl by d theta. No doubt. The concept here we are applying to derive the torque equation of MI instrument is, according to law of energy conservation, electrical energy input equal to change in stored energy plus mechanical work done. Then I calculated what is the electrical energy input. I calculated what is the change in stored energy. Then I calculated what is the mechanical work done. These three I substituted in this equation. Then we are getting the expression for deflecting torque. The deflecting torque equal to half I square into Dl by d theta. Understand? No. Quick. Now tell me, we know that in general in MI instrument what type of controlling torque we can use? Spring controlling torque we can use. Yes. That is, for spring control, what the relation? Yes, for spring control, what is Tc equal to k theta? At steady state or final deflection of a pointer, at steady state or at final deflection of a pointer, what is the condition? Tc equal to Td. What is Tc? K theta. What is Td? Half I square Dl by d theta. Then what is theta equal to? 1 by 2k I square into Dl by d theta. This is the deflection of a pointer in moving iron instrument. We are assuming that spring control. We also assume that gravity control, we can derive the final deflection. But here I am calculating in general which controlling torque is preferable, spring control. That's why I taken this. Theta equal to 1 by 2k I square into Dl by d theta, where k is the spring constant. Clear? Okay, this is the deflection of a pointer. If Dl by d theta equal to constant, one observation here. Yes. If Dl by d theta equal to constant, then what is the theta is proportional to I square. Theta is which one? Output. I is which one? Input. this input-output relation is linear or non-linear? Non-linear. The input-output relation is non-linear. Hence, therefore, hence, in MI instrument, yes, scale is non-linear. In MI instrument, scale is non-linear. The scale of the MI instrument is non-linear. Okay, this is what the deflection of point in MI instrument or the deflecting torque equation. This you remember. This is a concept of how to derive the deflecting torque equation of MI instrument. But for competitive point of view, based on this torque equation, I want to list out some points that is important. See the observation from torque equation. Let's concentrate on what are the observations from torque equation. Yes, observations. Yes. What is the deflecting torque TD equal to? Yes, TD equal to half I square dl by d theta. This is the deflecting torque equation of MI instrument. The deflecting torque TD equal to half I square dl by d theta. Therefore, one observation is in moving iron instrument, the deflecting torque is proportional to square of the current. But in the case of PMMC instrument, what is the observation? That is, deflecting torque is proportional to current. But in the case of moving iron instrument, it is proportional to square of the current. Second observation. We know that what is theta equal to 1 by 2k into I square into dl by d theta. Theta equal to 1 by 2k into I square into dl by d theta. That is, if dl by d theta equal to constant, then theta is proportional to I square. Then this response is called square law response. This is called pure square law response. If one quantity is proportional to square of the another quantity, then that response is called square law response. Then if you draw the characteristics between theta versus I in the case of moving iron instrument, then it is which characteristics we can get? Parabola. These characteristics are nothing but a parabola characteristics. In moving iron instrument, the theta versus I characteristics are parabola. Okay. Sorry. Get the characteristics like this. Parabola. That's why up to initially the change in value is very small. In some portion it is nearly linear. In upper portion it is more change. That's why this design is cramped design, that is crowded. But this design is linear design. But this design is expanded design. Expanded. That means in the case of moving iron instrument, in the design of scale, lower scale is cramped. But in some portion, that nearly middle portion of the scale is linear. But in upper portion, the upper portion of the scale is expanded scale because of these characteristics. Understood? That's why theta is proportional to I square, then it is nothing but a square law response. But if any instrument completely will satisfy like this, then we can say that is pure square law response. If any instrument satisfy the pure square law response, that instrument is a true RMS meter. But this is satisfied with the assumption of dl by d theta equal to constant only. But in the case of MI instrument, we are using iron core. Because of that iron core, the dl by d theta is always not equal to constant. If dl by d theta is not equal to constant, is not exactly proportional to I square. Once it is not exactly proportional to I square, then square law response is distorted. When the square law response is distorted means it is not a true RMS meter, because it is not satisfying the exact square law response, perfect square law response. Yes, that means but practically dl by d theta is not equal to constant. Hence, if dl by d theta is not equal to constant, then square law response is distorted. Square law response is distorted. Hence, it is not a true RMS meter. MI instrument is not a true RMS meter. It is not a true RMS meter because it is not satisfying perfect square law response, but practically dl by d theta is not equal to constant. If dl by d theta is constant, then only this is proportional I square, then it is a perfect square law, then we can say that it is a true RMS meter. Clear? Okay. This is one observation. The third one. Listen please. We are telling that theta proportional to I square. Theta is proportional to I square means scale is non-linear or non-uniform or cramped scale or crowded scale. Non-linear or non-uniform scale means lower portion is crowded and upper portion is expanded. Like that we can decide. Yes, one more observation. But I told already, in nonlinear scale also we can make some portion is linear. Then how to make some portion is linear, that you will see. By designing which condition, if dl by d theta equal to constant, then that scale is nothing but a theta proportional I square. Then to make portion of the scale is linear, then which condition must be satisfied? What is the condition for linear? That is theta proportional to I. Then I equal to some constant c into theta. But actually what is theta equal to? 1 by 2k I square into dl by d theta. Okay, this is the actual characteristics of MI instrument. This characteristics we want to convert as a linear characteristics. If you want to make this as a linear means, substitute the condition for linearity in this equation. Then what is theta equal to? 1 by 2k into what is I? C square into theta square into dl by d theta. From this, what is theta into dl by d theta equal to? Theta into dl by d theta equal to 2k by c square. 2k by c square is constant. That means to make the portion of the scale is linear, based on which condition we can design the scale. To make the portion of the scale is linear, theta into dl by d theta equal to constant. Based on this condition, if you design the scale, then that portion becomes linear. That is, what do you mean by theta into dl by d theta equal to constant? See, to make the portion of the scale is linear, theta into dl by d theta equal to constant. Theta into dl by d theta equal to constant means if theta tends to 0, dl by d theta tends to infinity. It's correct, because dl by d theta is proportional to 1 by theta. If theta tends to 0, dl by d theta tends to infinity. Theta tends to 0 means lower portion. That's why this condition will not satisfy. This condition will not possible, is not possible in lower scale. Is not possible in lower scale. Is not possible in lower scale. That means we never design the lower scale as a linear scale. Why? If you want to design the lower scale as a linear scale means we want to maintain dl by d theta is infinity. You want to maintain large value of change in inductance. That is not possible. If theta tends to infinity, dl by d theta tends to 0. Then this is theta tends to infinity means ideally infinity means practically high. Practically high deflection means upper scale. Is not possible in upper scale. Is not possible in upper scale. Possible in upper scale. In upper scale also we can't design as a linear portion, linear scale. Therefore, theta into dl by d theta is constant, is maintained nearer to middle scale or down to 1 by 10th of upper scale, down to 1 by 10th of upper scale. That portion only we can design as a linear scale. Theta into dl by d theta is constant, is maintained nearer to middle scale or down to 1 by 10th of. Let this is upper scale, down to 1 by 10th of upper scale only we can maintain as a linear portion. That portion only we can design as a linear, because this condition will not satisfy. Satisfying this condition in lower scale is difficult. Satisfying this condition is upper scale is also difficult. That's why this condition is mainly satisfied under the middle portion of the scale. Hence that portion may be linear. Then if you draw the characteristics between theta versus dl by d theta, then this you write as a fifth observation. Tell me. We know that dl by d theta is proportional to 1 by theta. That is, theta into dl by d theta equal to constant. Yes, theta into dl by d theta equal to constant. If you draw the characteristics between dl by d theta versus theta, let in this portion of the scale 10% of scale 0.1 theta, up to this we don't maintain theta into dl by d theta is constant. That's if theta into dl by d theta is not equal to constant means then dl by d theta is constant means theta is proposed. That is, dl by d theta is constant. Can maintain like this. But beyond this we can, then what are the characteristics? Dl by d theta is proportional to 1 by theta means what these characteristics? One quantity is inversely proportional to another quantity means which characteristics? Rectangular hyperbola. Then we get the characteristics like this. Up to some portion dl by d theta is nearly constant. Then this is rectangular hyperbola. Okay, these are rectangular hyperbola characteristics. up to some portion only, in this middle portion of the scale only, 1/10th of this one only we can maintain as a linear. Okay, but beyond this, dl by d theta is not the theta into dl by d theta. Dl by d theta is constant. It is a constant value. Then we can get the, like, these are the characters, rectangular hyper. The theta versus dl by d theta characteristics are rectangular hyperbola. In the middle portion only linearity is possible. In upper and lower portion not possible. The upper scale is expanded scale. Okay. The lower portion of this scale is, this is cramped scale. This is cramped scale. Okay. Okay. This about what is the dl by d theta versus theta characteristics in the case of MI instrument. This is the fifth observation. See the sixth observation. Tell me. We know that in moving iron instrument, internally it consists of only one coil. Because of only one coil, internally it works on the principle of self-inductance. That is, because of one coil, it works on the principle of self-inductance. It works on the principle of self-inductance. Principle of self-inductance. Then seventh observation. We know that due to iron core, the moving iron instruments are more subjected to hysteresis errors. Yes or no? Then due to hysteresis effect, then moving iron instrument shows the more, for same values of input, MI instrument shows the higher readings in descending order as compared to ascending order. That I given in the case of hysteresis. In the concept of hysteresis, characteristics of, in the undesirable characteristics of instrument, I already explained hysteresis now. Due to hysteresis of instrument, the values in descending order is more than as compared to values in ascending order. That is, MI gives that is for same values of input. For same values of input, MI gives higher readings. MI gives higher readings in descending order. As compared to ascending order. Yes, as compared to ascending order. Because of hysteresis. Okay, due to hysteresis of instrument, this we are getting. Then last one, eighth observation that you concentrate. Eighth observation. The first observation is TD is proportional, that you already note down, no problem. Eighth observation. Okay, I already explained, even in moving in PMMC instrument also these observations I given. In PMMC instrument also I given the observation. During operation of instrument or during switch on the supply. Okay, during operation of instrument or during switch on the supply, if one spring is damaged or both the springs are damaged, what is the reading of the meter? Where I explain three cases. Here also I want to explain the three cases. But for example, let us assume that in a moving iron instrument, initially scale at 0. Initially pointer is at 0. During switch on the supply, if any one spring is damaged and open circuited, now what is the position of the pointer? What the meter will shows? But here in moving iron instrument, springs is not carrying the current. When springs is not carrying the current, then which torque is present? deflecting torque is always present. But if any one spring is damaged, then what the controlling torque will becomes, then Tc dash equal to Tc by 2. Then Td greater than Tc by 2 na, whenever Td greater than Tc by 2 means the pointer goes to the full scale deflection. See the difference between MI and PMMC. In PMMC, springs carrying the current. During switch on the supply, if spring is damaged, no current, no deflecting torque, always pointer shows the 0 reading. But in the case of MI instrument, even though spring is damaged, still there is a current through the coil now. Because of current through the coil, which torque is produced? Deflecting torque is produced. If any one spring is damaged, controlling torque is reduced. Then deflecting torque is greater than controlling torque, then the pointer goes to the full scale deflection. That is first observation. Second observation. Let assume that already pointer is at X reading. We already started the experiment. Already pointer is at X reading. Now, if any one spring is damaged and open circuited, in this case also, if any one spring is damaged and open circuited, then what the controlling torque becomes? Tc by 2. But even though spring is damaged, which torque is present? Deflecting torque is present. Why? Always there is a current through the coil. Then again deflecting torque is greater than controlling torque na, then the pointer goes to full scale deflection. But it will never come to the again 0. Because deflecting torque is greater than controlling torque, and that's why the pointer goes to the full scale deflection. That is the second case. Third one. For example, let us assume that already pointer is at X reading. That means during measurement. Already some X reading means we are doing the experiment, already we are measuring some value. During that, if both the springs are damaged and open circuited, what is the Tc equal to? 0. That is the controlling torque equal to 0. But which torque is present? Deflecting torque is present. Because of the deflecting torque, again pointer goes to which deflection? Full scale deflection. That's why for all the three cases, only one answer. But in the case of PMMC instrument, 3 individual answers are there. But in this MI instrument, for all the 3 cases, only one answer. That means during switch on the supply or during the operation. If one spring is damaged or both the springs are damaged, always pointer shows the full scale deflection, because springs is not carrying the current and always deflecting torque is present, and deflecting torque is greater than the controlling torque. Hence the always pointer shows the full scale deflection. That is right, 8th observation. That means in MI instrument, during switch on the supply or during the operation. Yes, during switch on the supply, or during the operation. During switch on the supply or during the operation. If one spring is damaged or both the springs are damaged. If one spring is damaged and both the springs are damaged. Always pointer shows the full scale deflection. Always pointer shows the full scale deflection. Because why? Because springs is not carrying the current. Springs is not carrying the current. Springs is not carrying the current. When springs is not carrying the current, hence springs is not carrying the current, and TD, and in all the cases, TD greater than TC. That's the reason why the pointer shows the full scale deflection. Okay, these are the observations from torque equation of MI instrument. TD proportional to I square, theta equal to 1 by 2k into I square into dl by d theta. Then theta is proportional to I square, that is a square law response. It is not a true RMS meter. Then scale is non-linear. To make the portion of this scale is linear, which condition must be satisfied? theta into dl by d theta equal to constant. Then if you draw the characteristics between theta versus dl by d theta, then you can get rectangular hyperbola. This portion is crowded and some portion is linear, and this portion is expanded, the some portion is expanded scale. Like this you can design the scale. Because of only one coil, it works on the self inductance. We know that for same values of inputs in increasing and decreasing order, the meter gives more values in descending order as compared to ascending order because of hysteresis. Then during switch on the supply or during the operation, if one spring is damaged or both the springs are damaged, always pointer shows the full scale deflection because springs not carrying the current. In all the cases, TD greater than TC. Okay, this about what is the observations from torque equation of MI instrument. Okay, this mainly concentrate. Okay, this is one important concept with respect to any commutative point of view, that you concentrate on torque equation and you also concentrate on deflection of a pointer. Theta equal to 1 by 2k into I square into dl by d theta. This one more point to remember, whatever the input is applied to MI instrument, then it measures which value? RMS value. If any equation is given, if any circuit is given, if any waveform is given, applied to the MI instrument, it measures the RMS value. That point to remember. For this I am giving one note. For example, if the circuit is given like this, based on this also we will see some classroom workbook later on. The circuit is given like this. The supply is AC. This half wave diode rectifier. This Vs equal to Vm sin omega t. Vm sin omega t. Let this is V1 voltmeter. This is V2 voltmeter. Let this is PMMC. And this is already based on PMMC, you already solved the problems. Okay. Then what the PMMC measures? Average value. What is the average value of half wave diode rectifier? Vm by pi. Then what is the RMS? What is the MI measures? RMS value. What is the RMS value of half wave diode rectifier? Vm by 2. Like this you can answer. For example, if the circuit is given like this. Okay. This ammeter. This also ammeter. This is purely inductive load. This also half wave diode rectifier. Okay, this is V1 voltmeter, this is V2 voltmeter A1, this is A2, let this is PMMC, this is MI, this also PMMC, and this is MI. If it is given like this, then what is Vs equal to Vm sin omega t you take? Vs equal to Vm sin omega t. Then in this case, what the PMMC measures? Average current. What is the average current in purely inductive load? Vm by omega L. Okay, that you will see derivation in our power electronics subject. This what is the MI measures? RMS current. What is the IRMS equal to? That is root 3 by 2 into Vm by omega L. All these derivations will come in our power electronics. Then what the PMMC measures? PMMC measures average value. What is the average voltage? Pure inductor? 0. Then what is the MI measures? RMS value. What is the VRMS equal to? Vm by root 2. But even though it is a half wave rectifier, we can get Vm by root 2 because of pure inductive load. Okay. Another note, for example, it is given like this. This is full wave rectifier, full wave diode rectifier. Full wave diode rectifier. Let Vs equal to Vm sin omega t. Vs equal to Vm sin omega t. And let this is some resistive load. We are connected to voltmeters, voltmeter 1 and voltmeter 2. Let this is PMMC and this is MI. Okay, if it is a resistive load. Now, what is the PMMC measures? Average value. What is the average value of full wave diode rectifier? That is average value of full wave diode rectifier is how much? 2 Vm by pi. 2 Vm by pi. Then what is the RMS value of full wave diode rectifier? MI measures RMS value. Vm by root 2. But don't confuse. Sir, even though it is half wave diode rectifier, here you taken Vm by root 2, here also you taken Vm by root 2. But it is because of purely inductive load. In purely inductive load, the output voltage waveform is again sinusoidal. For sinusoidal RMS value is how much? Vm by root 2. Here we can get full wave rectifier output. Then what is the RMS value? Vm by root 2 we can get. Like this. That means if any circuit is given, if any waveform is given, if any equation is given, MI means which value take? RMS value. PMMC means which value can take? Average value. Already in the basic requirements of indicating type instrument, which instrument measures average value, which instrument measures RMS value, already given some list. That also you concentrate. Clear? Okay, this about what exactly deflecting torque equation of MI instrument. In the next session, we will continue with how to extend the range of MI instrument. That is MI as a ammeter and MI as a voltmeter. Then after that, I will discuss some errors in MI instrument. Then you go for the classroom workbook questions. With that, MI instrument will be complete. Okay. Thank you. Concentrate. In the next session, we will continue.